Hi everyone, this is the second video in our Chapter 12 Gases series here, so that's what we're currently looking at. We initially began by looking at the different units of pressure, some conversions, and our different individual gas laws, Boyle's law, Charles' law, leading up to our combined gas law, very handy, and some other principles, looking at Gay-Lussac's study and combining that with Avogadro's law dealing with volume and the amount of a gas. Okay, so now we're going to kind of put some more of these ideas together, and we're going to look at the density of a gas. Now, density can be factored into our ideal gas law equation, which was, again, a very important equation. We left off the video number 1 there. So a couple things to take note. We need to recall that moles of any substance is equal to the mass of that substance divided by the molar mass. Performing that calculation always tells you the moles, and of course that can be rearranged to solve for any one of those three variables. We can substitute symbols. N is our abbreviation for moles that we use. Mass, we typically have a lowercase m, and molar mass we sometimes have as a capital M. We'll stick with that notation here for right now. So if we look at our ideal gas law, N was one of our variables in our ideal gas law. So we could take N and substitute in, mass and molar mass. So we get an ideal gas law that looks like this. PV equals our mass divided by molar mass times RT. Right? All we have to do is substitute those variables in for N. So we might not know the exact moles, but hey, if we knew the mass here, if we knew the mass and we knew what substance we were dealing with, well then we'd know what the molar mass was, and we could easily figure out the moles. And we could plug that directly into the equation, and we could do all this math separately. That's kind of up to you. Alright, well, since we're also talking about density, you guys should know the density formula. Density is equal to mass over volume. Okay, so now we have another relationship with mass in it. We can actually substitute in these variables into our equation as well. So that leads to another modification. Density equals mass over volume. Well, that would be equal to, let's move the pressure over to this side. Pressure times molar mass divided by RT. All I did was do a little bit of algebraic rearranging there to go from this equation here, substituting in our density, mass, and volume. Right? We have mass and volume here. So if I move those to the same side, I get m over v, and I can substitute that in for d. And then pressure, molar mass, R, and T are over here. Okay, so important thing is here we see that the density of a gas is related to its pressure, the molar mass, and the temperature. Okay, there's a relationship there. R, of course, is our constant, so don't really have to worry about a relationship there. But we can see what happens when we start messing with these different variables. So let's take a look at that right now. Okay, so I'm going to rewrite that same equation I had earlier. I'm going to stick it right here in the middle. And let's see how all these variables are related. If I take something like the volume, okay, if I say, okay, my volume of my gas is getting bigger and bigger. So if my volume is getting bigger, volume is in the denominator, so that means if volume gets bigger, denominator gets bigger, guess what? That leads to a smaller density. Okay, we can start doing this for a lot of these variables. Okay, I could go to pressure. Okay, and say, okay, what if the pressure of my gas is increasing? If I have a greater pressure of my gas, well, pressure is in the numerator, so the bigger my numerator gets, the greater my density gets. Okay, and likewise, we can look here at temperature. If the temperature of a gas keeps getting larger, heating your gas up more and more, well, again, bigger denominator makes density smaller. Okay, I suppose, well, we can do one more. Let's look at mass. Okay, so if I have a really small mass of gas, that's going to lead to smaller density. So we can anticipate and predict what's going to happen to each of these values depending on what's changing and what's staying the same, which is really great to do in gas law problems as you're going through calculating them. Before you even do any calculations, you can think to yourself, okay, what's changing? How is it changing? Is it getting bigger or smaller? And what's that going to do to my final answer? It's kind of a great way to check to make sure if your final answer comes out reasonable or unreasonable. Usually if you make any sort of calculation error, you get the exact opposite, right? If I'm using this equation somehow and I know my volume is getting bigger, it's changing, then the density I have should be smaller than whatever I started with. Well, if you calculated one that's larger, guess what? You probably did it wrong. So always do those kind of quick predictions before diving into the calculations of the problem. Okay, I'm going to start a new page here and let's look at an example problem. Okay, example here. Let's say we have a 0.105 gram gas. And let's say it has a pressure. I'll just capitalize P for pressure, abbreviate. Let's say it has a pressure of 561 millimeters of mercury. And its volume is 125 milliliters. So let's say I've got it contained in a 125 milliliter container. And that gas is at a, no, I meant for that to be a decimal. Oh boy, that's a big eraser. Okay, 20, oh geez. Small eraser. Okay, that's much better. Okay, so get rid of that. Sorry. 23.0 degrees Celsius. 3 sig figs there. Okay, period. And our question is, what is this gas's molar mass? Question mark. Okay. If you guys want to, you can pause the video right here, give this one a shot. Alright, let's look at our answer. Well, I've got 561 millimeters of mercury. I typically don't like the pressure unit millimeters of mercury, at least I don't like doing math with it, so I like to convert. So that's what I'm going to do first. I'm going to take 561 millimeters mercury and convert that into ATM. ATM is my personal preferred unit, and so there are 760 millimeters of mercury is equal to 1 ATM. So a simple division there gets me an ATM pressure of approximately 0.738 ATM. Okay, that's a little bit better. I can use that with my ideal gas law stuff and my gas constant of 0.0821. All right, well, you can see we have all of our different information here. Little tip with doing gas law problems, making a list of your variables, that can help a lot. Pulling the information out of the problem can really help. If we pull out our information, we see that we have a pressure of 0.738. We just solved for that. That's our ATM. I can take that and I can multiply that by my volume of 0.125 liters. Remember, our gas constant is in units of liters, so we have to make sure that our volume is in liters and that they match. Right? It's always important that the units match. So a quick conversion to our liters, moving our decimal over 3 spots, we get 0.125. That's going to be equal to my moles, N, multiplied by my ideal gas constant, 0.0821. I'm going to leave the unit off, just be, well, you know what, I'm going to try to cram it in here. We get liter atmospheres per mole Kelvin. I fit it in. One way to remember that, I always say latum molk, just kind of pronouncing it latum, L-A-T-M, latum, M-O-L-K, molk, latum molk. Stupid, I know, but hey, remember the stupid stuff, right? Okay, last thing, temperature. We need to convert that into Kelvin, so we need to take our degrees Celsius, which is 23, and add 273 to that. And we get 296 Kelvin. Fix that. It's an ugly K. Whatever. Okay, cool. Now all we have to do is run through this calculation, and we wind up with a mole value of 3.80, 3 sig figs, times 10 to the negative third is what I got. But of course, moles is not what we're looking for. We're looking for molar mass, and molar mass is equal to our mass, which we're told is 0.105 grams per mole, and our moles are 3.80 times 10 to the negative third moles. Grams per mole, right? Just check the units. Grams per mole, and that's our molar mass. So now all we have to do is divide those two numbers, and we get something approximately 27.7 grams per mole is our answer. So that's our molar mass of our gas. Now I kind of did this calculations separately. I used our ideal gas law in the form that we're used to solve for moles, and I did the molar mass calculation later. You could have used a different form of the ideal gas law that we just went over, incorporating mass and molar mass into the equations would be absolutely just fine, and you could have easily just solved for m as one equation. That works as well. There are a number of different ways to go about solving this mathematically. Whichever way works for you, stick with it. Okay, now let's look at factoring this into equations and reactions, chemical reactions. Alrighty. There is a fantastic diagram on page 555 of our textbook, Gases and Chemical Reactions. The diagram really outlines the kind of thinking process when going through conversions and solving for something. Remember, moles is key, right? Especially with the reaction. How to get from one substance to another, you got to get to moles. So if you look at that diagram, I'm not going to write out the entire diagram here, but I will just make a quick note, tell you guys again. Diagram on page 555. Okay. And the key point to the diagram in a lot of our chemistry calculations, in order to compare different chemicals, reactants to products, reactants to other reactants, products to products, anything in a reaction, you need moles! Exclamation point. You got to have it. So it's all about getting to the mole. If you look at that diagram, if we're given the mass of a substance, well, then we can use molar mass to get to moles. If we're given the molarity of a substance and a volume, we can get to moles that way. We've done that before. And now we know if we're given properties of a gas, pressure, temperature, volume, we can use our ideal gas law to get to moles. It's all about getting to the mole. And once you have the moles of one substance, you can figure out the moles of another using mole ratio. That's what that diagram is showing you. Okay. So definitely take a look at it and make sure you understand what it's trying to show you in terms of the calculations and the thinking process behind going through any of these calculations. Okay, let's dive right into an example. Let's say we're given this balanced chemical equation. Sodium nitride. This can decompose and produce sodium solid and nitrogen gas. Okay, and we're asking the question, what quantity of sodium nitride, actually no, this is sodium azide, I'm sorry, sodium azide, that's what N3 minus is called, is needed to produce enough gas to fill a 45.5 liter container, say bag, at 829 millimeters of mercury at 22.0 degrees Celsius. Very common question, right? In fact, this was the chemical that was originally used in airbags. There'd be a small amount of sodium azide sitting in the airbag, waiting to deploy. And when the car detected a rapid deceleration, this would rapidly decompose instantly. And would have to fill up and produce enough gas, right? Who cares about this? Who cares about the solid? Have to fill up enough gas to basically fill up the airbag before your face hits it. So it would have to break down and decompose super fast. And you would have to produce enough nitrogen gas to fill it up so that your head could hit it and there'd be enough of an impulse. Yeah, there's a physics word. Or I might be using that wrong. Never mind, I'm not going to use it anymore. You have to slow down, right? You can't fill it up with so much nitrogen gas that your face bounces off of it and then you get whiplash and probably don't survive. And you also can't produce too little of a gas where your face goes through the airbag and then into the steering wheel. That's also not good either. So it has to be just enough to provide that nice slow down of your face moving forward. Okay, enough about that. Let's do the math. Let's try to figure out how much sodium azide we need in our bag to produce enough gas. Okay, so if you notice all the starting information, we're given lots of information about the gas. We know we need a 45.5 liters, we know it has to be at this pressure, and we know it's at this temperature. We have enough information about our gas to solve for the moles. So that's what we're going to do first. I'm going to start a new page. Okay, so here's our new page. First, how many moles of gas? Okay, to do that, PV equals nRT. That's a terrible equal sign. Okay, there we go. Again, pressure, you want to convert that into ATM. When you convert your millimeters of mercury to ATM, you should wind up with something like 1.09 ATM. We know we need 45.5 liters of gas. Moles is our unknown. R is our gas constant, 0.0821. I'm going to leave the unit off. And convert our temperature into Kelvin, and we get 295 Kelvin, I believe. All right, if we solve for nitrogen, we wind up with 2.05 moles of nitrogen. That's our only gas in our reaction. Okay, but that's not what it's asking. It's not asking how many moles of gas we want to produce. We want to figure out how much of the sodium azide, our starting material, our reactant. So to do that, we got to do a little bit of our typical Stoich. So the second thing we need to do is ask ourselves, how many grams of sodium azide are needed to produce our 2.05 moles of N2. So we have our 2.05 moles of N2. And we know our mole ratio, if we look back at our balanced equation, is 3 moles of N2 for every 2 moles of NaN3. And one more conversion to grams. 1 mole of NaN3 is equal to, I got 65.01. That 0.01 is probably pretty silly. 65.0 grams would have been fine. And we get our amount of our sodium azide. We solve that, and I got 88.8 grams of NaN3. 88.8, that's a lot of 8s. Reminds me of the Back to the Future. 88 miles per hour, right, was what the DeLorean had to get up to go back to the back. All right, I'm getting off track. Anyway, all right, that's our problem, right? So that's kind of the basis behind how gas stoichiometry works. Okay, using our ideal gas law, whenever we have our amounts of our gas needed, and we can figure out moles, and then we can use our Stoich to get back to some solid. This whole process can go in reverse too. If we knew we had 65.01 gram, or I'm sorry, if we knew we had 88.8 grams of the NaN3, we could work backwards and figure out, hey, how much gas will we produce? Well, we can figure out how many moles of that gas we would make and plug that into our ideal gas law, and we might solve for volume, something like that. That's a very common problem. Okay, let's run through an example just like that. Let's say we have a reaction N 2H4 is aqueous. When it reacts with oxygen gas, produces 2 moles of liquid water. It's a terrible L, but you get the idea. And it produces N2 gas. Alright, now our question is, if you have 180 grams of N2H4, how much of the O2 gas, what is the volume of O2 that will react? And it's going to be reacting at 750 millimeters of mercury, and it's reacting at 21.0 degrees Celsius. Okay, so what is the amount of O2? That's what we're solving for. And by amount, for gases, we're talking about volume. That represents the amount, right? We don't typically refer to gases in terms of grams. We can, but it's just not typical. Volume is how we refer to the amount. Okay, cool. Well, if you want to pause here and give this one a shot, go for it. If not, let's go ahead and get started. First thing we're going to do, we need moles of our starting material. So, that says material, by the way, material. I'm not going to try to erase that. All right, well, we've got 180 grams of our reactant, N2H4, and we need to convert that into moles. So N2H4 is 32 grams per 1 mole of N2H4. Now, that pretty much gives us our starting material. Okay, and you know what, let's just go ahead and go right into moles of our other substance. Well, we got to ask ourselves, what's the other substance we're looking for? That's oxygen. We want to find out about oxygen. So, I'm going to switch colors here. And we can use our mole ratio. So what is it? Back of our equation, it's a 1-to-1 mole ratio. 1 mole of N2H4 produces 1 mole of O2 gas, or reacts with, I should say. Reacts with 1 mole of O2 gas. So right here, we can solve for our grams of O2. So we need moles of starting material, and then moles of other substance. Oh, that's not how you spell substance. I need a bigger eraser. Oh. There we go. Okay, sorry. Substance. Okay. So let's go ahead and solve for that. I'll put an equal sign down here, get some more room. And we solve, and we get something close to 5.6 moles of O2. Is what that comes out to be. All right, so now we have our moles of O2. Now we need to figure out its volume. Okay, so to figure out its volume, we got to use our ideal gas law. So with our pressure at 750 millimeters of mercury, that's practically 1 atm, but it actually comes out to be 0.99 atm. Our volume is our unknown. I don't know why I used the parentheses. That's okay. And our moles is 5.6. Gas constant 0.0821. And our temperature in Kelvin comes out to be 294. So we solve for our volume. And I got something close to 140 liters of O2. Okay, so it's pretty much the reverse process of the previous example that we did, right? We're starting with some solid, or a solution, right? It said aqueous, I know, but it gave us the mass of that reactant, and our job was to figure out what's going to be the volume of the gaseous reactant. Okay, So we'll move on from examples there. Let's talk about a new idea, one that is called partial pressures. Okay, for that, we focus on Dalton's law. Okay, Dalton's law basically says that the total pressure of any mixture of gases is equal to the individual pressures of each gas. So on and so forth. That can go all the way up to infinity. Okay, so it's basically what he's saying. He's saying the total pressure here is equal to the partial pressures of each individual gas. Okay, so if I have a pressure of one gas mixed with the pressure of another gas, add those two together, that gives me my total pressure. If I have 3 gases, yay, 4 gases, 5, so on and so forth. Okay, here's a key little point here. It doesn't matter what the gas is. The pressure does not depend on the identity of the gas. So it doesn't matter what gas it is. Oxygen, nitrogen, hydrogen, helium, neon, doesn't matter. Okay, who cares? The only thing it depends on, pressure, it's only going to depend on is moles. Okay, and of course this is only true if temperature and volume are constant. Okay, temperature and volume are all changing, well then pressure is probably going to change, so on and so forth. So the more moles of my gas that I have, the more partial pressure that gas will apply. Okay, so if I have 2 moles of one gas in a container and 1 mole of another gas, well then the pressure of the 2 mole gas will be twice as much as the pressure of the 1 mole gas. Add those two pressures together and you get your total pressure. Alright, let's wrap this idea up. Okay. Let's say a container contains 3 gases. Let's call those gases A, B, and C. Okay, so our pressure total, using the ideal gas law, would be equal to the moles of A plus the moles of B plus the mole of C. And that'd be multiplied by the rest of the ideal gas law, which would be RT, and I moved volume here to this side, right? Because again, this whole partial pressure idea does not depend on volume and temperature. They're staying constant, okay? But it does depend on here the total number of moles. All right, so here this whole thing represents my total moles, which is basically equal to my total pressure. Let me go ahead and rewrite that. Our total pressure is equal to N total times RT over V. Okay, so if I know the amounts of each of those individual gases, well then I can just convert them all to moles, add them all up, and I'd be dealing with the total pressure of the entire system. Another little side equation here, stemming off of this idea with moles and the relationship of moles, we have this idea called mole fraction. Mole fraction, which is given the symbol capital X, not a lowercase x. So let's say the mole fraction X, let's say we want the mole fraction of our substance A, well then that would be equal to the moles of A divided by the total moles. Right? Just like any fraction, right, is a part out of a whole. Okay, so mole fraction is the part, which would be the moles of A, divided by the total moles, right? Not too shabby. Well, we can rearrange this equation, and we can write it a little bit differently. If we rearrange it, we get our total moles is equal to the moles of just A divided by the mole fraction of just A. Okay, we do that, and we can sub this idea into our ideal gas law, and get this lovely little idea. We can say the partial pressure of just A is equal to the mole fraction of A times the total pressure. This comes in handy. Okay? If I know my total pressure of my system, and I know how many moles I'm dealing with, well, guess what? Multiply those two ideas, our mole fraction, right, which is represented here, multiply that together, and I get the partial pressure of just that one individual specific gas. So it does come in handy. Okay, one final thing we have to discuss about is this concept of collecting gases over water. So for that, we're going to kind of need some visuals here. Okay, if we take a look at the diagram here, so we're titling this Collecting Gas over H2O. Okay, so look here, we see what actually is a typical scenario with how we would collect a gas from a reaction. Okay, we have here a reaction between zinc metal and hydrochloric acid. Nice little single replacement reaction that produces hydrogen gas. Okay, now hydrogen gas, you'll see, is going to be funneled through this tube, and we're going to funnel it into an inverted beaker of water. Now when this reaction started, water was filled all the way up to the very top. In a perfect situation, there wouldn't be a single molecule of air inside this beaker. It would be completely filled to the top with water. Okay? Then when you start producing the hydrogen gas flows through the tube and displaces the water. Okay? As more and more hydrogen gas builds up in here, the water level gets pushed down. The water level will get pushed out and go into this big tub, and the water line in the tub then would rise slowly. Okay? Okay, so that's how this whole scenario works. Now, here's one piece of information, if you can tell from the diagram. The hydrogen gas is represented by these two small spheres connected, right? H2 gas. You can see it flowing through the tube. There is a very small amount of water molecules that are actually evaporating. Okay, so it's not just pure hydrogen gas that's being collected, or any gas for that matter. Water is always there. So whenever you see a problem that tells you that something was collected over H2O, you have to understand that there's going to be a mix of that gas that you're collecting plus water vapor. So here it says hydrogen plus water vapor. There's always going to be a little bit of H2O molecules that are in the gaseous state as they're evaporating off the surface into this area of gas. Okay, so we'll worry about that in our calculations here in a minute. So this whole entire process would continue until you've collected enough gas, whatever you want to collect, some significant amount. All right, doesn't really matter. I'm going to try to redraw the scenario. Once you're done collecting your gas, what you would do is you would raise or lower, trying to redraw the tub here, you would raise and lower your beaker of water. You know what? I don't like this. I'm not going to go with the. I'm not going to go with a 3D image like the diagram. We are going to draw it very flat. Okay, so here's our big tub. Here is our beaker, right? So big tub, beaker. You would raise and lower the beaker, okay, and as you did that, the water level inside would actually rise and fall as you moved it, and you want to get it so that the water level in the tub matches the water level in the beaker, okay? So you want to match water levels. When you do this, okay, this ensures that the pressure applied outside here, the pressure that's pushing down on this water, is equal to the same total pressure inside the flask. Okay? So, make a quick note. pressure outside equals pressure total inside. Okay, so that's why that final step would be done. Once you're through collecting all your gas, you raise and lower this beaker until these two water levels are exactly the same. Then you would know that, hey, whatever the outside pressure is, which you could get off of a barometer, the weather, anything like that, telling you what's the atmospheric pressure, would be equal to the pressure inside. Now, you wouldn't have any instrument inside here to measure the pressure, which is why you have to do this step, making sure that if this is a lab that you're conducting, you have to make sure these two water levels are the same. If it's just a simple problem, then whatever the total pressure they tell you, obviously, is your total pressure. But if you're conducting this lab or designing this lab, you have to make sure these two water levels line up, and then you can assume that this outside pressure of the atmosphere is equal to the total pressure applied by all your gases inside. They are exactly the same. Okay, so a few more pieces of information about these types of problems. Our total pressure is equal to the pressure of our gas. In this example, that's the pressure of H2, okay, plus whatever the pressure H2O is applying. Now the nice part is, so these are partial pressures, right? The partial pressure of gas and the partial pressure of H2O. Add those together, you get your total pressure. The nice part is there is a table of partial pressures of water. Let's say here, partial pressure of H2O is in Appendix G. Okay, Appendix G in our textbook has a nice table that tells you what the partial pressure of water is at different temperatures. So it's pretty straightforward. Whatever temperature that this lab is being conducted at, or whatever temperature the problem is telling you, you just have to look up the H2O pressure at that temperature, and bingo. What you would do is you would plug that pressure in for H2O. The total pressure you would know from the problem. All you have to do is subtract those two values, and you get the partial pressure of your gas in question, the gas you actually want to do some calculations on or know something about. Okay, you don't care about the partial pressure of water. You want to get rid of it, right? So whatever the total pressure is, that total pressure is not the same as the pressure of the gas. You have to first subtract off the partial pressure of H2O, and that gives you the pressure of your gas. Okay, that wraps up this video. This section here, we'll stop right there, and we'll wrap up with kinetic molecular theory and some thoughts on diffusion and effusion about gases. So we'll do some more practice with these. Definitely keep going through your problem sets and make sure you guys work through any homework assignments. Any questions, let me know. Feel free to bring them up in class or tweet or email or ask questions on the discussion board for our class. Okay, great. Take care, guys.
Made with Doodlecast Pro.